Hi, Mr. Townsend here. In this video, I'm going to I'm going to answer all the questions in this paper from 2023. This demonstrate understanding of chemical reactivity. That is the achievement standard. That's 2.6, I think. Achievement standard 91166. I hope it helps. Just leave a comment if you have any questions and look out for the other videos I've done on the rest of the papers in the exam. Don't forget to like, share and subscribe if you find these videos helpful. Leave any comments if you have any questions or if you notice any mistakes. Thanks again. I hope you enjoy the video. Well, I hope that it's useful anyway. Right, okay, let's look at this exam, this achievement standard 91166 2023. That's chemistry 2.6, and I'm going to go through this exam and demonstrate how we might answer the questions. Okay, so question one, the first question that we've got here is they've told us that there's an acid found in the human stomach called hydrochloric acid, so it has a pH value of approximately 1.5. Calculate the concentration of hydronium ions present in the hydrochloric acid solution. So what they're wanting us to do here is just do a simple calculation. We're going to go to our resource sheet and find the formula, and the formula here that we need is the hydronium ion concentration equals 10 to the negative of the pH as an exponent. And so we put that into our calculator. If you've got a scientific calculator, this will be the inverse of the log or a shift log. Put the plus minus button and then 1.5, enter it, and you get this answer of 0.0316. Put the units in moles per litre. This is only an achieved question, so they're not going to mark you down if you don't put the units, but it's good practice just to put them in anyway. Okay, so the next question says that you have these fast-acting paracetamol tablets. They contain sodium hydrogen carbonate. This is which reacts with the stomach acid. The equation is below. So this is sodium bicarbonate or baking soda. It reacts with the hydrochloric acid. It makes sodium chloride plus carbon dioxide plus water. Now, some students want to investigate how long it would take for the baking soda and the paracetamol tablet to react in the human stomach. They conducted an experiment where a 0.25 gram tablet of sodium hydrogen carbonate was reacted with the excess hydrochloric acid at room temperature. That's 20 degrees approximately. The volume of carbon dioxide produced was plotted. So here's our graph. Now let's look at our graph. We've got two sections they're going to ask us to talk about, A and B. We remember that it is the steepness of the gradient that indicates how fast the reaction is going. So obviously the reaction is going a lot quicker in point A than it is in point B, and then at the end it's stopped. Now we have to, when we go to the first question, it says with reference to collision theory, that means we're going to talk about collisions between reactants. Explain why the steepness of the line changes as it proceeds. Refer to sections A and B in your answer. Right, so in section A, there is a high concentration of hydrochloric acid particles. That means there will be a high frequency of collisions, or you could say there are lots of collisions per second. High frequency collisions is a nice just statement we can put in here. So there are a lot of successful collisions per second, and we will have a quick reaction and a steep gradient. So I've kind of explained A. Now let's explain B, and we'll just do it in comparison to A. So as the HCl reacts, its concentration decreases, so the frequency of successful collisions decreases, reducing the reaction rate. I should have said in part B, the concentration decreases, but that's pretty evident from what I've written here. Okay, the second part, so how are we marking this? So we've got 2 points here. You're going to get an achieved for one of the points, and you're going to get a merit if you cover both. Part 2 here. The internal temperature of a human stomach is 37 degrees. Remember that the reaction was carried out at 20 degrees. Explain why the student's experiment would not give a good indication of how long the tablets take to react in the stomach. Well, of course, the temperature is different. So we're going to refer to collision theory and talk about why we would expect to get a different result with a different temperature. Obviously, it's warmer. We would expect it to react faster, but we have to give our reasons, and there are two reasons we always give for temperature. So the first thing that we have to indicate is the temperature is hotter, okay? So there's going to be more kinetic energy. The particles will have more EK or kinetic energy. That means they move faster, and there will be more frequent collisions with the HCl particles and the sodium hydrogen carbonate particles. So this is the first point. Because temperature is hotter, there's more kinetic energy and they move faster. Second point, that is an independent point. Try not to link it to the first one. Also, because you have more kinetic energy, more of the particles will have the energy required to overcome the activation energy, and they will have more frequent successful collisions. So you're talking about there's a whole bunch of particles, and more of them have enough energy now because the whole solution is warmer to overcome the activation energy. Because of these points, it's going to react faster in the stomach. Okay, so usually when we do a temperature explanation, we're expecting to get an excellence from this part. So we've recognized as long as you've put down the increasing temperature, increasing kinetic energy, you get an achieved. If you link the frequency of successful collisions to the particles moving faster and the kinetic energy, that's a merit. Or if you link the increasing kinetic energy means that more particles have the energy required to overcome the activation energy and there are more successful collision, that's a merit. If you put both of these points down, that's your excellence. And look, most papers are going to have this temperature question, so you should really practice this up. Let's go on to the next page. Okay, so next page looks like I've already put the actual equations in here, but so let's read up the top here. While the acid found in the stomachs is hydrochloric acid and is considered strong, propanoic acid is considered weak. So this is propanoic acid here. With reference to these two acids, explain the difference between a strong acid and a weak acid. Include equations in your answer. Well, of course, here's my equation for the hydrochloric acid. It's strong, so it has a direct arrow going from left to right. We say it fully dissociates, or it fully interacts and breaks apart with water when placed in water. Therefore, it's going to produce a very high concentration of H3O+. That's why it's a strong acid. CH3COOH, or propanoic acid, sorry, not CH3, CH2COOH, is a weak acid. That means it partially dissociates, or it sets up an equilibrium in its reaction with water. So for every maybe 1,000 of reactants, we have one product. So we only produce a small amount of product, and we use the phrase partially dissociates. So this is just an achieved question here, and they're looking for either the equations are correct or you've said fully and partially dissociate correctly for the strong and the weak acids. Now we need to compare and contrast the pH and the conductivity of these two acids, which they say are equal concentrations. So if we have a high concentration, when a solution conducts electricity, it means it has a high concentration of ions, because the ions are what transfer the charge from one electrode to another. I'm just putting that statement in so we're clear about that for a start. HCl, because it fully dissociates, and we say it conducts electricity because it has a high concentration. We've already set up here it fully dissociates. We could write that again. So it has a high concentration of H3O+ available to transfer charge. Okay, because HCl fully dissociates, the Cl and H3O+, they are a positive and a negative ion. They can transfer charge because of these high concentrations. Also, because there is a high concentration of H3O+, because it fully dissociates, this solution will have a low pH, because we remember that a high concentration of H3O+ results in a low pH. The propanoic acid, however, it only partially dissociates. That means there's a very low concentration of H3O+ and CH3CH2COOH. That means that it's going to have a much lower concentration of ions, so it's going to be a very poor conductor of electricity. It's also going to have a lower concentration of H3O+ ions, so its pH is going to be relatively higher. It's still going to be less than 7 because it's still going to produce acid hydronium ions, but it's not going to be as low as 1. It's going to be something around about 3 or 4. So this is an achieved, a merit, and an excellence question. If we understand that the conductivity is related to the concentration of ions present, that's an achieved. If we link the degree of dissociation, that is that we say it fully dissociates, so there's a high concentration of ions in both solutions, then we've got a merit. Or if we said one of these points correctly, like HCl fully dissociates, produces lots of ions, therefore the ions are able to conduct electricity well. If we covered all points, then we get an excellence. And for this whole first question, we've just finished the whole question. The way that this works is if you get 2 E's, you get an excellence. If you get 2 E's with a minor error, so here something we left out, we would get an E7. If we get a combination of 4 M's from all of our questions, we'd get a M6, and so on and so forth. Okay, let's go forward and look at the next question. Okay, question 2. Let's have a look at it. Question 2, it's a wee bit confusing this because it's using 2 similar words, but the molecule lactose, which is a sugar found in milk, is slowly broken down in the stomach by water into the sugars galactose and glucose. The rate of reaction is significantly increased by the presence of an enzyme called lactase. Remember, enzyme is a biological term for a catalyst. Okay, so the lactase, don't be confused with the lactose, is the enzyme that helps break down the lactose. The lactase is not used up, so it's another hint that there is our catalyst. So the first question, identify the role of lactase in the reaction. It acts as a catalyst. Okay, the next thing they want us to do is complete an energy diagram by drawing 2 lines to show the reaction with and without the addition of lactase. So we're going to show the reaction with the activation energy before having the catalyst and after. So here is an example of a line with showing the activation energy hump, and this is without the catalyst, and here's the dotted line with the catalyst. Notice the height of the activation energy is significantly smaller with the catalyst because it provides an alternative pathway. So here we have to explain on the right hand side, well, let's just check what this is. Just an achieved question for drawing these and labeling it correctly and putting the catalyst here. The part 3 here, it says explain how the rate of reaction is altered by the presence of the lactase enzyme or the catalyst, referred to collision theory, and activation energy. So there's a couple of key phrases we're going to use here. The key phrases are going to be activation energy and alternative pathway. So lactase is a catalyst and provides an alternative pathway. That's what this dotted line is here on the left for the reaction with less activation energy. So there is less energy initially required to get over the bump. So that's less activation energy. Because of the alternative pathway, more of the particles have the energy that is required to have a successful collision. So there will be more successful collisions or a higher frequency of successful collisions per second. Okay, sorry, not per second, higher frequency successful collisions or more successful collisions per second. There will be a higher reaction rate. Now this is achieved merit and excellence question, and you can see from here that basically if we put down that the catalyst gives an alternative pathway that is lower in activation energy, achieved. If we link the higher rate of reaction energy to the higher rate to the lower activation energy, we get a merit. If we include all of this, we're going to get our excellence. So again, we're going to expect every paper to we're going to have to explain why a reaction goes faster with a catalyst, just like we had to why it goes faster with temperature. So the next part is to do with the equilibrium, and it's we have to think about equilibrium different than rate of reactions. So the steam methane reforming process, which is the means of producing hydrogen gas, is shown below. So take methane, they add water, and it produces carbon dioxide plus 3 hydrogen gas. We have to write a Kc expression for this. So a Kc expression, remember, is us drawing the reactants over the products, These reactants, we don't need to draw their states, that is the gas states in the brackets, but we do have to put the coefficient that's in front of every number as an exponential, and they all have to be placed in square brackets like so. Notice the 3 goes as the exponential, the symbol is put in the square brackets, and the products are always put over top of the reactants. So this is just an achieved mark. This is something that they fundamentally expect you to do every time and do well. Okay, let's go to the next slide. Okay, so explain using equilibrium principles why removing hydrogen gas as it forms is an advantage to the production of hydrogen gas. Well, why is it good to remove the hydrogen gas as it forms? Well, if we look at this equilibrium equation, we can see that the hydrogen gas is on the right-hand side. It's a product. And if we remove a product, because this is a dynamic equilibrium, the system will oppose the change by favoring the forward reaction. And the forward reaction will produce more hydrogen gas. So that's why it is beneficial to take the hydrogen gas away, because every time we take it away, it's going to make more. So that's an achieved and a merit question. Yeah, I mean, we just, as long as we say that I guess the key phrase is always try and chuck in that every time that a equilibrium system reacts, it's reacting to oppose a change. It's Le Chatelier's principle, right? And if we have that point and the point that forward reaction is favored producing more hydrogen, that gives us the merit. So here's a really hard question. This is maybe the hardest question in this paper or in the papers, and that is they're talking about Kc and that it increases. Now the Kc doesn't increase if we change the concentration, and it doesn't increase if we change the pressure. But if the temperature is changed, the Kc can either increase or decrease. It's saying if we have a higher temperature, and that is we increase the temperature, the Kc increases. Now, using equilibrium principles, we have to say, does that mean that the forwards reaction is exothermic or endothermic? If the temperature increases, the reaction opposes this change will be favored. So we've stated Le Chatelier's principle, that is that if we make a change to the equilibrium, the opposite will happen to oppose the change. So if we increase the temperature, the reaction that opposes it. Now the reaction that opposes an increase in temperature is the endothermic reaction, because it absorbs the extra heat that is added by the increased temperature. So now we've said if we increase the temperature, the endothermic reaction is going to be favored. The endothermic reaction is favored. That means, okay, so we have to think about this. If the Kc equals the products on the top and the reactants on the bottom, if the Kc is increased, that means we have more products. And the endothermic reaction is favored. Okay, so there's more products. That's the forward reaction. When we make more products, the endothermic reaction is favored. So therefore, the forward reaction that produces the products must be the endothermic reaction. There is at least 4 links in here. This is easily an excellence question. It kind of goes almost above and beyond an excellence question. So you should, if you can do this question well, then you're doing the whole paper well. This is an excellence question. And if you can do part of this, so if you can recognize that if the temperature increases, then the endothermic reaction is going to be favored. If you can recognize that if you increase the Kc, that means there's more products compared to reactants, they're going to give you achieved. If you get 2 of those points, you merit. And if you put it all together and work out that the forwards reaction is endothermic, that's your excellence. Right. Okay, so the same for this question that we just finished, question 2, is that you want to get an E8, you need 2 E's. If you want to get into the merits, right, you need 3 merits at least for an M5 or 4 merits for an M6. So there's quite a busy question. You've got quite a bit to do to get good marks here. Let's look at the last question. Okay, so last question. Okay, that makes sense. It's an acid-base question because we haven't really done a lot on acids and bases in this paper so far. So here what we've got is a an equilibrium equation, but it's to do with acids and bases. So both water and hydrogen carbonate are amphiprotic. That means they can act as both an acid and a base. The reaction of hydrogen carbonate with water is shown below. Identify two acid-base conjugate pairs. So what we're trying to identify are the two pairs. So here is one substance. So this is the hydrogen carbonate and the carbonate. Those two are a pair. Now the reason why they're a pair is they're very similar, and the only difference between them is the difference in one hydrogen and a positive charge. Now once we've identified that these two are a pair, the one with the extra hydrogen is always going to be the acid. So we can write down the acid-base pair by putting the hydrogen carbonate first and the carbonate second, the acid and the base. Let's look at the other pair. The other pair is water and hydronium ion. They are very similar. The only difference is one hydrogen. Notice the hydronium ion has the extra hydrogen, so it's going to be the one that we write as the acid, and the water is going to be the one we write as the base. And there we go. Here's our acid-base pair. Now, so we get an achieved for this. We need to get both these pairs correct to get this. This should be something that fundamentally you put a lot of effort in, and you're always going to get this right. Okay, because we just need to make sure we get this achieved question. Now we say that 0.1 mole per solution of the weakly basic salt. Okay, that means that this is a salt that when it breaks apart, one of these components is a weak base. Now sodium is always neutral, so the component's going to be what's left. Now when we have a weakly basic salt or a weakly basic acid, there are always two equations. The first equation is the dissociation of the ions, or the breaking apart of the ions in water. So it's going to look like this. So we've got sodium ethanoate breaks apart into ethanoate and sodium ions. Then the component of it that is the weak base, because this is a weakly basic salt, is going to further go and react with the water and the solution it's placed into. Now because it's a weak base, it's going to accept a proton plus water and turn into the weak acid ethanoic acid, and the water is going to turn into the OH minus. Now it says here, wait, we must get an achieved for doing those two. Actually, we only need one correct equation to get the achieved here. So the next point is a solution of potassium hydroxide of equal concentration has significantly higher pH than this solution. Can you tell me why? This is similar to the question earlier on in the paper, but okay, let's calculate. Well, it doesn't say tell me why. They just want us to calculate it for a start. So they want us to calculate the pH from a concentration of a strong acid. Now, if we look at potassium hydroxide, you see that each potassium hydroxide produces one hydroxide. So the concentration of hydroxide is equal to 0.1. In order to calculate the pH, we're going to have to convert the concentration of hydroxide into the concentration of the hydronium, or the H3O plus ion. We do that by going to our resource sheet, and we look at our resource sheet and we find the equation that is 1 times 10 to the negative 14 equals a hydronium ion concentration times hydroxide ion concentration. And that's this one on the right hand side here. We need that. We're going to rearrange that. So what we do is basically divide both sides by the hydroxide concentration. The hydroxide ion concentrations cancel out, and we get this equation here. Now it's always in this form. The way that it rearranges, it's always the hydronium ion equals 1 times 10 to the negative 14 over the hydroxide ion. Or if you have to find the hydroxide ion, it's a different type of question, it always equals 1 times 10 to the negative 14 divided by the hydronium ion. So it's always the ion that you want is 1 times 10 to the negative 14 divided by the concentration of the ion that you have. So we put that number into this calculation, and we work out that the concentration of H3O plus is 1.00 times 10 to the negative 13. Now, remember, the reason we did that is we can't calculate the pH without knowing the concentration of the hydronium ion. because we have to do the negative log of the hydronium ion, not the negative log of the hydroxide ion. So we put the negative log in here, and the answer we get is pH. Remember, no units for pH, and try and do it to 1 decimal place. So we've got 13.0 is our pH. Awesome. So because this involved 2 steps, you do 1 step correctly, it's an achieved. You do 2, it's a merit. So even if we had done this, if you'd done the first part wrong and got a wrong answer here for hydronium ion concentration, if you did the pH calculation right, you get an achieved. But to get the merit, you have to do both correct. Why is there a difference in a pH between the 2 solutions? Well, okay, it's pretty straightforward, really. So this is what we said before. Potassium hydroxide is placed in water, it fully dissociates. That means it breaks apart in potassium ions and hydroxide ions. Whatever the concentration of potassium hydroxide is the concentration of OH minus. So therefore, it's going to have a high pH. And in this case, it had a pH of 13, right? But when the ethanoate ion reacts with water, it only partially dissociates, and we know that because we have an equilibrium arrow. So we produce a lower concentration of hydroxide ions. Because this is lower, correspondingly, the H3O plus concentration is going to be higher, and we're going to end up with a smaller pH than 13. See, we have 18.8. Here's our equation here to help explain this, but it was over on the other page. Now, this is an achieved, merit, and excellence question. And you can kind of identify here that if you realize that the higher pH, the 13 pH, is to do with the concentration of OH minus ions, or the ions of OH minus being higher, that's an achieved. If you can link the higher concentration to it fully dissociating, or the lower concentration to it partially dissociating, that's merit. If you can actually put it all together and say, look, if I have a high concentration OH minus, I get a low concentration of H3O plus. Well, sorry, if I have a higher concentration of OH minus, lower concentration of OH plus, and I get a high pH. Or if I have a lower concentration of this, then my H3O plus is higher, you're going to get the excellence point. I mean, the bit where you have to relate it to the H3O plus is a bit tricky, I get that, but that's what they wanted for excellence. They want you to say, okay, the ethanoate ion, it has a lower OH concentration, therefore it has a higher H3O plus, and if you have a higher H3O plus, you have a lower pH. That's why it's 8.8 instead of being 13.0. Okay, the last questions of the paper. Here's a KC expression. We're going to expect at some point in the paper they're going to give us a calculation to do with the KC expression, and this is it. So what the first step they want to do is kind of interesting. They want us to, instead of drawing a KC from the equation, they want us to draw the equation from the KC. So we have to remember that the COF2 is a product, and the 2 that's the exponent is going to go in as a coefficient. The 2 species on the bottom are a reactants, and they're going to go on the left, and we end up with this equation. So this is an achieved point. Okay, so we're just doing the opposite of what we may have usually practiced. We're just putting back into we're writing an equation from an expression. Now this is where it gets a bit more complicated. So they said the reaction carried out at 1,000 degrees. Now the only reason they've said that is at the top they've said the Kc equals 2 at 1,000 degrees. So they have to reference the same temperature, because if it wasn't the same temperature, it would be a different value for Kc. Then they said if the concentrations of CF and CO2 were found to be equal to one another, and COF2 is found to equal 0.105, calculate the concentration of CF. Now this is interesting because this is quite a higher step of algebra here. We have to equate 2 values. So we write down the Kc expression, and then the first thing I'm going to do is say that CF4 equals CO2. Oh, and no, it wasn't the first thing I did. I substituted in the two numerical values, and these are the two unknowns. But remember, they told us that CF4 equals CO2. So if CO2 equals CF4, the bottom of the equation equals CF4 squared, because CF4 multiplied by CF4 equals CF4 squared, and this CO2 equals CF4 because they told us that in the equation. So now we have an equation that we can rearrange. We're going to put the CF4 on the left hand side, and we're going to move this 2 down to the bottom, and we're going to solve the equation now. So CF4 equals the square root of 0.15 squared over 2, and we get an answer of 7.42. Now, the difficult part here is equating these two values. This is doing some more difficult algebra than we would normally do. If you did one step correctly, they gave you an achieve. If you did a mistake, let's say you forgot to square root, right? So you just divided 0.105 over 2, then you got a merit. If you got it completely correct, you got an excellence. Last question is, what would be the effect of increasing the pressure on this system? Okay, so this equation here, we haven't put in the states here, but actually if we look further down, we can see that CF4 is a gas, CO2 is a gas, and we have to assume that COF2 is a gas as well. Let me have a look here. They haven't told us it is, but I'm going to assume that it is. Maybe it's in the previous question. Okay, so let's assume that all of these particles are gases. Then what's going to happen is the pressure, if we increase the pressure, the equilibrium will oppose the change by favoring the reaction that produces the less gas particles. We'll put that statement down because that's always true, no matter what the equation is. So we're going to go in the direction of the less gas particles. This is going to give us an achieve point. And here I'm saying, as both the reactants and product sides have 2 moles of gas particles, neither reaction will be favored and the position of equilibrium will not change. If we look back further in the paper and we find out that COF2 is in fact not a gas, that answer would be different. But because I've just looked over onto this page that I'm on and I've made the assumption that this is the gas, then my answer is true. And look, it will be marked as true as well. And that there is the end of the paper. We get an achieve for one of those points, a merit for both, and then we're going to go through the same marking for this part of the paper, and that we need 2 E's to get our excellence. It's quite tricky looking at this question here. Because it's a wee bit trickier to get the E's in this paper. This paper had a threshold of a 19. You had to get 19 to get an excellence for this paper. Well, I hope this has been useful, and if you want some more help with other exam papers, me going over them, make sure that you go and look at the links or that I have on my site, YouTube channel, and follow those to look at the other papers. Thank you. I hope that video has been useful. If you have any questions, don't forget to put that down in the comment. I'll see if I can answer them for you. Don't forget to subscribe if you want to see some other videos that I have made about this, and give it a like if you found it helpful.